So again, I will go through some of the things that we did before very quickly, and then we'll focus on the new stuff, but hopefully this time in a more arranged way. So I think this is, I should have removed this from here. So I will skip those round and truncation errors. Okay. So we discussed last time already the set of linear equations and how they are represented in the matrix format, and then how you can solve that set of linear equations. Some of the things that I mentioned quickly, but we didn't really picture them, was things like upper triangular matrix, lower triangular, diagonal matrices, the identity, which is not just ones here, but zeros everywhere else. There's also something called banded matrix, which is a matrix with only certain number of diagonals symmetrically around the main diagonal, and the rest of the matrix is zeros. And it happens a lot also in linear systems that are modeling actual physical systems. That one has an easier algorithm to solve as compared to the algorithms that are used to solve the typical cases. Matrix operations, you already know those, how to multiply, how to inverse a matrix, all these things, you already know them. Now representing a linear algebraic system. So you have the matrix A, which is the matrix of the coefficients of the different variables on the different equations. And then that matrix is multiplied by a vector of the unknowns. And on the other side, you have a single vector of the constants or the constant values, okay? And that is representing this linear set of equations, linear equations. If you want to solve that in MATLAB, I told you that the right, it's called the left division symbol, right? This one is used to perform the operation of solving a linear equation composed of a matrix A, a set of unknowns X, and a vector of constants B, by saying X equals A left division over B. And this means B divided by A, which simply means the inverse of A multiplied by, that's how MATLAB interprets it. It's the inverse of A multiplied by B, okay? However, the nice thing about the left division is that it does a test on the matrix A, and if it finds that the matrix is diagonal, or if it finds that the matrix is upper triangular or lower triangular, or if it finds out that it is a banded, it uses immediately the efficient algorithm to solve that system. While if you say X is equal to the inverse of A multiplied by B, so if you try to solve using this command, you actually instruct MATLAB that it has to calculate the inverse and then multiply it by B. So it doesn't really look for any other alternative algorithms. So generally speaking, this is much more efficient because MATLAB is going to automatically check the matrix A and apply the most efficient algorithm depending on the characteristics of the matrix A, right? Which does not necessarily mean that it's going to compute the inverse. While here, MATLAB will compute the inverse and multiply that with the matrix multiplication operation with B, okay? We went through the Gauss elimination, so I'm not gonna go through it again. And then just shows you here that one of the, if you have really a set of linear equations and you want to solve them, if it's like a couple of equations, 2 or 3, probably it's much easier to plot them and then see where they intersect, and that's actually what your solution, right? But if you have more variables and more equations, then that plotting would not work, and then you need to apply the methods that we discussed. These are also the different situations of singularity. This is the situation of two parallel lines, which means that you cannot, it's called what? Inconsistent, right? So you cannot really find the solution. This is the case where you have infinitely many solutions because the two lines are aligned to each other. Of course, all of this is two equations and two variables, right? And this is something called L condition. So notice that the two lines are not really aligned to each other, but the difference is very slim. And this means that, remember I told you last time that the L condition is one of the problems because the MATLAB itself might feel that this is a singular case. Just because the difference between those two equations is very slim, such that it might look like it's this case, or it might look like it's this case. Okay? So this is what's called an L condition situation. It is a situation that can be uniquely solved, but because of the precision and truncation error, when you are trying to apply numeric techniques, they might not work in this situation. You have to be careful in those situations how to deal with the numeric calculations and the errors. Yes?
Special way to solve this issue?
Yes. There is no special way to solve it generally speaking, but there are algorithms that works better for the L condition situation as opposed to the normal situation. There are algorithms that probably they take longer, they are not the most efficient, but they are more stable in terms of the error accumulation. So you always have to do that trade-off. If the system is quite healthy, which is opposed to ill-posed, right? In that case, you are looking for the algorithm with the fastest possible way to reach the solution. But if the system is ill-posed, then probably you have to be careful and pick something with very high accuracy so that you can avoid getting a singular solution. Okay. Now, in determinants, we all know determinants, but the nice thing here is that it shows you an approach to solve the set of linear equations using determinants, which is called the Kramer's rule. And the Kramer's rule, I mean, it's written here, but it's easier to describe it on the slide directly. So the Kramer rule says that if you have, for example, this set of linear equations that you see here, okay? And you have x1, x2, x3 in each one of them, three equations. The system is well defined, so there is no singularity or anything, and now you are looking for the solution. Then you can solve by calculating the determinant of the whole system. This is the determinant of the matrix A. And then if you want to calculate, for example, x2, the value of the variable x2, then the way to do that is to go and calculate something called D2, the determinant D2, which is the same as this, but you replace the second column here, which is the coefficients of the variable x2, with the constants, right? Calculate the value of this determinant. If you divide the value of this determinant over the determinant D of the matrix A, the result is going to be immediately x2, right? So that's called the Kramer's rule, and you can do the same for x1, you can do the same for x3. But the difference is going to be, you calculate D1, which is going to be this, but you replace the first column with the constant, the b's, right? To calculate x1, and if you want to calculate x3, you replace this one with the constant in place of the third column, and so on, okay? Now, it might look like this is an efficient algorithm, but no, because calculation of determinants is a very computationally expensive operation, right? Lots of multiplications and additions when you calculate any determinant, right? So it's not really, it's nicely structured, and it looks like it's two steps, but in terms of the number of flops, the number of operations that you have to perform, it's actually very expensive computationally. Okay? And then we talked last time about the Gauss elimination and the naive version of Gauss elimination, which just keeps everything as is and pivots immediately and do the forward elimination and the back substitution in two stages. And we said that this might meet an issue, which is sometimes the pivot becomes 0, which means that you cannot really divide over that, and you face a divide by 0 situation. In order to avoid that, we talked last time about the partial pivoting, right? And there is something also called complete pivoting. Before going into those partial and complete pivoting, this is the basic Gauss elimination. And even though it might look silly, but I advise you to try to write this program right now, and start playing with it. So can we take 5 minutes so you can kind of, I mean, there are lots of comments here, so it's up to you to write the comments or not. But the most important thing are the different steps, okay? So try to write this program and try to start playing with it. Okay. But how about, okay, it's something that you have to keep in mind for every single algorithm that you study. There is one aspect which is the accuracy, right, of the algorithm. And the other aspect, by the way, do you think there are any truncation issues associated with the Gauss elimination? Why? Do we approximate anything? Because truncation comes from approximation, right?
The values are very close to 0, for example.
That's a precision issue, right? So, so for the Gauss elimination algorithm, that's an example of an algorithm where you don't have any truncation errors because there is no approximation of anything, right? You are representing the system exactly as it is. You are performing the exact operations that are performed in manual theoretical calculations of the Gauss elimination. The only thing is you are using finite precision because of the computer. Right? So if you have numbers with large number of digits, you might lose some of those digits. But this is not truncation, this is precision issue, okay? So the errors here might happen only because of numeric precision. That's on the error side. The other thing that you always need to look at when you are doing numeric calculations is complexity, or sometimes they call it the efficiency of the program. That's not the most common name. They typically call them complexity or the number of calculations that you have to perform. Okay? For the Gauss elimination, you have to perform a total number of calculations, which is in the order of 2 multiplied by n cubed divided by 3. The constants do not matter that much in this case, but it is something of the order of the cubic of the dimension of the matrix. So if you have a matrix with a dimension 10 by 10, then this means that the number of operations that you are doing is in thousands. If you have a matrix of dimension 100 by 100, then this means that the number of operations that you are going to perform is going to be in the millions, right? Because 100 raised to the power 3 is millions, and then multiplied by some constants, 2 over 3, whatever, but it is in the range of millions, okay? So this shows you, typically, we care most of the time. This is not bad, by the way, okay? Typically, we care most of the time about the highest order if it is represented in polynomial. The worst case scenario in terms of complexity that you end up here with, for example, 2 to the power n. That's called exponential complexity. This blows away very quickly, right? A non-polynomial complexity, a complexity that becomes in the exponent. So the number of operations relies now on your parameter being in the exponent. That's called exponential complexity, and this is the worst case scenario. Because that one, imagine that you go from, for example, the example that I said, you go from 10, let's say it's 2 to the power n, okay? And you go from 10 to 100 in terms of the size of the matrix, right? So you go from 2 to the power 10, which is what? Approximately 1,000, 1,024, right? So that's approximately 1,000, to 2 to the power 100. How big is this? Yeah, so it's not no longer millions, not even billions, it's probably above that, right? It was going in the trillions stage, right? So, but if it was polynomial like here, it just goes from 1,000 to 1,000,000, right? Which is still somehow doable, right? So that's something to watch for all the algorithms, the accuracy and the complexity or the number of operations that you have to perform, okay? Now this is the discussion about the pivoting and the partial pivoting. We have discussed that before. Again, unfortunately, looks like all the programs that I got here were Python programs, so I will replace that before posting the slides. So this is the program, and I will get that from the M files, and I also share the M files with you. They come actually with the book, so no problem. Sharing them, they're not mine, they're not someone's property or anything. So this is the case where before pivoting, you actually select the row with the maximum parameter in the column of pivot, and you put that as up in the scale. You move it up instead of the other columns. That's called partial pivoting. There is an operation called complete pivoting or full pivoting, which doesn't only do that, but also does some column replacement. But typically, numeric-wise, in terms of accuracy and in terms of number of operations, in terms of stability of the system, the gain is very small. So people either use just the naive Gauss elimination or the partial pivoting. Rarely they do the column switching to get to the full pivoting situation, because the gain from that is not too much. And you have to keep track which variables you move in location. Because when you move columns, it means that these are the parameters. For example, if you move the third column, these are the parameters of x3, right? And then you bring them to the first, for example, then you have to keep in mind that now the first column is x3. It's no longer x1, so you have to keep track of that. So it becomes very complicated, and the gain from that is not much in terms of numeric efficiency and accuracy. Another very special case that can be solved with Gauss elimination and other approaches as well is the special case. Remember, I told you that the case where you have a banded matrix in the matrix A. This means that in every single equation, you don't really have all the variables existing in the equation. In this case, in every single equation, you have only 3 variables. This is the tri-banded, right? Or they call it tri-diagonal, right? So in every single equation, you have only 3 variables, okay? And by the way, just you have to be clever, right? Sometimes this is the case, but they are not ordered to show you a tri-diagonal or tri-banded, right? So you just reorder the equations, right? Moving rows around is something that you can do. If you notice that in all the equations, there are in every single one of the equations, there is only 3 variables or only 4 variables or something like that, then you know that this eventually might look like a banded matrix, and in that case, just reorder them so that you can get that representation. Okay? You can imagine that here, if you, for example, if you want to perform the Gauss elimination, that's for example, you don't really need to use, for example, this row to eliminate anything except only the row after it, right? So there is nothing beyond. In this case, you only need to use this to eliminate the one right after it, and that's it. No need to do anything here because they are already zeros and so on. So you can see that the number of operations is reduced significantly. So even if you use the Gauss elimination as is, you still save a lot of calculations in these cases. Okay. Again, this is an example in Python, unfortunately. Remember last time we talked about the factorization, the LU factorization, where you go, and now I will show you why the LU factorization makes the solution of the linear equation easier. So the whole idea of the LU factorization is that you go to the matrix A and you try to represent that matrix as a multiplication of a lower triangular multiplied by an upper triangular, okay? And then you start utilizing this kind of nice structure to those 2 matrices to solve the linear equation with less number of operations, with much less number of operations, without jeopardizing anything in terms of the efficiency. Now, there is a famous algorithm which is doing the LU factorization, and that algorithm is called the Cholesky algorithm. It's a command in MATLAB that you can use directly. If you want to look it up online to know exactly how it does the LU factorization, you can. I'm not going to discuss how it works, the Cholesky algorithm. Our focus here is more into what the LU factorization gains you in terms of solving the set of linear equations, right? So let's go to the next slide that shows this in a very nice way. So you can see here in this slide that this is the original equation, right? You can see this easily, right? It's readable from your side, no? You see it now? Okay. So this is the original system. AX equals B, right? Now the B goes as is. Now imagine that we were able to break the A into a lower triangular and an upper triangular. Okay. Now we can write. Now don't forget that the actual formula is A is equal to LU. So the L comes first and then the U after that. So if you replace that with the equation here, you will end up with, instead of the A, you have LU and then multiplied by the vector X, right? Equals B. Okay? Now, look at this one where you have the L multiplied by something here, right? Correct? So you have the L and then something. Is this thing going to be a matrix or a vector? This thing inside the two square brackets, it's a matrix or a vector? It's a vector of what size? Same size of X, right? Because you have a matrix, for example, n times n, multiplied by a vector of n variables. The end result is going to be 1 times n, right? N times 1, right? So you end up with a vector. Call that vector D, right? Now that is a vector of unknown values because it includes the x's, and the x's are variables. They are unknown to you, right? So now if you solve and get some values for D, these values, they include the values of x, but they are not exactly the same as the values of x, right? So originally, imagine that you are trying now to solve this system. So you have a lower triangular multiplied by some unknown variables, call them D's, right? Equal to B. Now, in order to solve this system, right, it's much easier because now it's multiplied by a lower triangular, which means that you can start solving the first equation directly. So no need to do any Gauss elimination, right? You already have the first equation with one variable. You can get its value. And then the second equation to substitute the first. So you only need to do the forward substitution. You don't need to do any, you need to do a backward substitution. You don't need to do any forward elimination because it's already a triangular matrix, right? Now you get the values for D, right? Now those values for D becomes the constants of another set of linear equations, which is composed of what? Don't forget that this D, the values that you got as D, are actually upper triangular multiplied by x. So you can write another equation, U multiplied by x is equal to D, right? And these are values that you got from this step, right? You can substitute, you can put them as values here. You have the U, which is known already because you did the factorization. And then the only unknown becomes the X. Again, you have an upper triangular, you only need to do the forward substitution or the backward substitution, but you don't need to do any forward elimination, right? So now you solved without any elimination steps. It's just simple substitution. But of course, the LU factorization itself has its own complexity in terms of calculations. Still, the overall operation here, in most of the cases, is more efficient than doing the Gauss elimination, especially if the matrix A has nice symmetry to it. Okay? In the case of symmetric matrices that have nice symmetry to them, the Cholesky algorithm or the LU factorization becomes a very simple operation. Okay? So that's the trick why the LU factorization is something useful in terms of solving a set of linear equations. Any questions? No questions?
There is only precision error and LU factorization.
Everything that you do here is only because we don't have any approximation. All the operations are full operations, but the only issue, and we are not doing any iterations or anything, the only issue is our calculation has some limitations because of the computation, so it's only precision. Okay. So again, MATLAB has a command called LU that does the factorization for you, and it has also another command called Cholesky. So it's called Chol, C-H-O-L. And then you put the matrix, it will analyze that into upper and lower triangular, as mentioned before. This is the set of lines. I want you now to try this. It's nice to try this, okay? So this is the set of lines that you will do in order to do the solution in the way I described, right? You start with the overall system AX equals B, and then for that you do the LU factorization for the matrix A, and you get the upper and the lower triangular, right? And then you solve the equation L multiplied by D is equal to B, which is solved by saying D is equal to left divide L over B, right? And then you get the values of D, and then the next step, you get the x's by solving the equation UX is equal to D. And that's solved again by using the left divide. Why the left divide here? Because as I mentioned, it's nice in terms of figuring out the fastest algorithm to solve based on the representation of the matrix. So in this case, it will immediately figure out that it doesn't have to do any inversion or anything. You just need to do substitution value, right? Because you are using now try this. So define a matrix A, 3 by 3, and give it some numbers, put some numbers in that matrix, and also define a vector B, which is 3 elements, and put some numbers in that vector. Make sure that your matrix is not singular. Okay? So when you put the numbers, be a little bit careful. Or put the numbers, and if you find it singular, change them. Okay? Until you reach a non-singular matrix, and then try to write those 3 lines of codes and see how you can get to the solution. Cholesky factorization, I mentioned before that it's popular and so on. This is what's written here. It doesn't really talk much about it, but just shows you how in MATLAB you can perform the Chol command. So which one you used you used UL, huh? Try the same solution and use Chol instead of UL. انت used UL مش كده؟ try Chol كده شوف هيديك نفس الفاليوز ولا different values for the upper and lower. نفس السيستم بتاعك but yeah, just use Chol to factorize the A بدل ما تستخدم LU and see whether you will get the exact same upper and lower triangular matrix ولا في اختلافات. There are some differences or not. لا it gives you both if you use شغل المفروض بيديك الاثنين. It gives you both. I think if you write لو حطيتهم في brackets هيديك الاثنين ولا لا؟ هو عين الهيلب بتاع الكوماند look at the help of the command. which triangle. So you can say upper or lower. غالبا هنا التراينجل ده هتقول مكانه upper or lower. So you have to call it twice. يعني one time it gives you the upper, one time it gives you the lower. The default apparently is already the upper. If you don't specify which triangle, it just gives you the upper. Can you try type? اكتب شغل كده وupper وشغل ولور. ده upper lower triangular ولا ده الاثنين؟ ماشي upper lower ده تقريبا على طول.
ايه رايك في اللاين 3 اللي هو شول يس
انت use the same matrix like his 1 2 3 4 5 6 7 8 so strange. Anyways. Okay. Yeah, matrix inversion and conditioning. So again, one of the things that can be interesting to perform is the calculation of an inverse of a matrix, right? Because that's also a very expensive operation. And a nice observation mentioned here is when you multiply a matrix, so remember that the definition of the inverse is A minus 1 is defined as it's the matrix that which, when multiplied by A, will give you the identity, right? Now, remember that when you multiply two matrices together, or when you multiply a matrix with a vector, what do you get out of that? خلينا when you multiply two matrices together, okay? How can you decompose that into something simpler, related to the columns of the second matrix? Yes, of course. And then you can break down this operation into the matrix multiplied by one vector, which is the first column, right, of the second matrix, and then the matrix multiplied by another vector, which is the second column of the second matrix, and the last one, the last column in the result is the matrix multiplied by a third vector, which is the third column of the last matrix, right? Okay. So here it's trying to break it down into this definition, right? So the A matrix, so where is that? So don't forget that A times A minus 1 is the same as A minus 1 multiplied by A, and in both cases you get I, okay? Now, if you define the inverse as a matrix composed of three vectors, call them vector x1, vector x2, vector x3. So these, because you need to calculate A minus 1, so it becomes the unknown to you, right? And if you think of that matrix as composed of three vectors, the first column, the second column, and the third column, then you can formulate this equation, A times A minus 1 is equal to I, as three different equations. Each one of them has a vector of unknowns, which is one column of the inverse, right? So again, I hope this is clear to everyone. Do I need to explain it further or clear to everyone? Okay. So here is your A. Let's say we use a 2 by 2. That's a simpler case. A11, A12, A21, A22. Okay. And now this is multiplied by an unknown, which is x11, x12, x21, x22, and this unknown is the inverse of A. So A is something that I know. The inverse of A is something that I need to calculate. And then I know that the result of this multiplication is 1, 0, 0, 0, 1, 0, 0, 0, 1. That's by definition, right? I can break this. Now take this matrix, right, and multiply it by the first column here. What do you get? Sorry. And it's a 2 by 2. يعني it's 1, 0, 0, 1. مفيش zeros ثانية ولا ones ثانية. It's a 2 by 2. Okay? So if you take this matrix and you multiply it by the first column, what should be the result? This one, right? How do you get this column? It's this, the first column here. The first element here is supposed to be this multiplied by this, right? And the second element is supposed to be this multiplied by this. So this whole column is this whole matrix multiplied by this vector, right? Similarly, the second column here is this row multiplied by this vector, and the second element of that column, the second column, is this row multiplied by this vector. So you can show that this whole vector of the unity matrix is equal to this matrix multiplied by only the second column as a vector, right? So you can formulate this as, in this case, 2 equations. In the case of a 3 by 3 matrix, it becomes 3 equations, where the unknowns here are the first vector of the inverse matrix, the second vector, the second column or vector of the inverse matrix, and the third column of the inverse matrix. تمام? Each one of those is a linear equation that you can solve using any of the approaches that we talked about, right? The nice thing here is you have 3 equations to solve, right? And the only changing part of these equations is a constant. So here, this is a very good example where when you do the LU factorization, you save a lot of effort. Because when you do the LU factorization, you can use the same L and the same U for all 3 equations. You don't need to calculate it again, right? So it becomes only one overhead, and then after that, no Gauss elimination, no forward elimination at all. It's just backward substitution in all 3 cases, right? So now you can solve these, and by solving for x1, x2, and x3, these equations, you can actually get the inverse of the matrix. So that's one way to calculate the inverse, by posing it as a set of linear equations. Okay? And of course, when you are solving, you do not solve by getting the inverse of A. Because you can solve this by getting the inverse of A, but now you saved nothing, right? If you get the inverse of A here, you already solved the problem, so you don't need really to do anything. Again, it shows you here that you can use the LU factorization and perform the operation. Another important thing, or another important insight, in fact, it's not really that much related to numerical methods. It's a general insight, even though also it helps with numerical methods, which is called the stimulus response computation. In many cases, particularly those who work in control, so maybe this is relevant to mechanical and electrical engineering. I don't know if civil they do a lot of control or not, but mechanical and electrical engineering, they do a lot of control. Even chemical engineering, they do. You have a system which is represented by some interaction. That interaction is your matrix A. These are kind of the things that you put into the system. And then you have, describe the system, right? So they describe the internals of the system. That's the matrix A. And you have the constants, which are stimulus, some input that you put into the system. And the resulting out of that is going to be the states that you will be in, which is the unknowns, x's, right? That's called the response of the system. So the A represents the characteristics of the system. It's a set of constants that belong to the modeling of that system, how it looks like from a physics point of view. And then now you know how it's represented. It's represented by the matrix A. You try to put some inputs. These are the constants on the side of the right side of the equation. And the result that will come out of that is something that you calculate, which is going to be the set of unknowns, the response of that system. Okay? So this is the stimulus or the stimuli, and this is the response. And using this representation, you can calculate numerically the output that comes from a particular system by simply solving the set of nonlinear equations for different values of B, for different inputs, for different stimuli. If someone pushes this button, what's going to be the output? If someone increases the pressure on the process and reduces the flow, what's going to happen? If someone increases the temperature and increases the pressure to a certain value, what's going to be the output, and so on. These are all variations of the B's, right? The system is constant, it's represented by the fixed A, and whatever you will get is going to be the solution that you get out of that, which is the X's. Okay? This is going to represent the response of the system. And you can imagine if you are trying to simulate a particular operation, then you can use this representation, right? So your simulation program is going to be simply, it will include that matrix A that represents the physics of the system, and then the input to the function that does the simulation is going to be the B's, going to be put into the B's, and the operation of the simulation is going to be simply solving the set of linear equations by any of the approaches that we talked about, and will give you the response of the system. So you can use that to simulate the operation of a particular system. If the system can be represented using linear representation, that's not valid in all cases, right? Okay. Another thing that we do a lot in linear algebra is norms. The norm is kind of a measure of a size, okay? For vectors, there are several norms that we can calculate, and they are defined. Some of them are defined here. So the first norm, or the first order norm, or the sum, absolute sum norm, there is the Euclidean norm, which is the sum of the squares under the root. There is the infinite norm, or the maximum magnitude norm, which is simply the largest element out of the vector. So when you say the norm infinity, it means that you go to the vector and you pick the element with the largest value, okay? And there is something called the P norm, the generalized P norm. Of course, you can set the value of P to any of those values, or you can keep it something else other than those. And that is calculated by the formula that you see, that this is the more general formula for the P, the measure of order P, of the size of a vector, right? Question for you. Can you show how this maps to this? Or can you think how this maps? That's a math question. Has nothing to do with numeric. So we are saying that this is the more general case. If you put P equals infinity here, can you actually figure out how this maps to this? I'm not going to answer that. Try to look it up. Okay? But try to figure out. I mean, all the others are easy to do. So if you put P equals 1, you will get exactly the same as the sum absolute norm, right? If you put P equals 2, you will get exactly the same. Now, what if you put P equals infinity? Do you really know, can you really figure out why this becomes the maximum among all the elements? Try to think about it, and maybe next time we can discuss it. Okay? You can look it up also. Similarly, for matrices, not only vectors, there are norms. They are a little bit more complicated, but again, they are just a measure of the size of the matrix. There is the first norm is the sum over the columns, right? And the second, second norm is something called the spectral norm, and that is the maximum eigenvalue raised to the power, maximum eigenvalue of this matrix, the A transpose multiplied by itself. And then this maximum eigenvalue is raised to the power half. There is also the A infinity, which is the sum of all the maximums of the different columns. So for each column, you take the maximum and then you add them together. And there is something called the Frobenius norm, defined more or less like the square, the sum of the square of all the elements, right? So you take all the elements, you square them, and you go over the whole matrix, in rows and columns, okay? And those norms are only defined for square matrices. You cannot calculate those norms for non-square matrices. Now that brings us to the L-conditioned matrix or the L-conditioned system. So there's something called the condition of a matrix. It's a command in MATLAB. You can say condition, and then you pass it a matrix. And what it calculates is the norm of A multiplied by the norm of A minus. So the norm of A multiplied by the norm of its inverse, right? And the result of that is used to figure out whether your system is L-conditioned or not, or L-posed or not, okay? I don't remember, I remember that the larger this value is, the worse your system is. So if this value is large, it means that your system is L-posed, and it may give warnings like what you got, or may even, when you try to solve it numerically, may even give you a wrong answer, or might not converge as you wish, okay? So here are some commands. Again, the calculation of the norms and so on can be done automatically on MATLAB. You don't really need to do these calculations by hand or anything. And the last part of today is going to be about iterative approaches. I think you are already aware of most of these iterative approaches. So you can solve a set of nonlinear equations without really representing the equations in terms of matrices and using the matrix representation. You can use an iterative approach. In that iterative approach, for example, imagine that you have 3 equations in 3 variables. So what you do in that case is you try to form the 3 equations such that in each one you have one of the variables on the left side and everything else on the right side. So here you have the first variable, here you have the second variable, here you have the third variable, and the rest are all the other terms of the equation, okay? And then the solution goes as follows. You go for the first one here, right? And you just start by substituting any initial values for x2 and x3. And you get a value for x1. You take that value of x1 and you substitute it here with the initial value of x3, and you get a value for x2. You take that value of x2, you substitute it here with whatever you got for x1, you get x3. Now you have 3 new values for x1, x2, x3, right? You take those and you substitute the x2 and x3 that you got from the previous step here to get the new one, and then you take that with the previous, so the new one with the previous one for x3, you get the new x2, and then you take the current x2 and the current x1 to get the new for x3, right? And you keep doing this until you reach a point where your error is bounded. So how do you calculate the error here? You calculate the difference between the new values of x and the previous value of x, okay? In the absolute sense. And once that difference becomes very small, smaller than a certain value, you assume that this is enough for me to stop at this stage, okay? That's called the Gauss-Seidel method, and it's an iterative method, right? There's another one that we also mentioned the name of that one last time, the Jacobi, yeah. And Jacobi is different only in one thing, okay? Notice here we have been, I mean, this diagram also explains it in a nice way. Let me see if I can zoom it in a little bit. Right? So it shows you the 2 methods side by side, right? So if you want to divide them, the right side is the Jacobi, the left side is the Gauss-Seidel, right? So here notice that when we are calculating this, we have used the one that we got from the previous here, right? So as we move in steps of one iteration, we are using newer values, right? For the Jacobi method, it's not so. So we just assume a value for x2, x3, get x1, assume a value for x1, x3, get x2, assume a value for x1, x2, and get x3. So we start with a certain, for example, 0, 0, 0, 3 zeros for the x's, and then we use the 2 zeros of x3 and x2 to calculate some new value for x1. We still use the 0 and the 0 even for x1 to calculate a value for x2, similarly to calculate a value for x3. And then we take those new ones and we substitute them into the new set of iterations, right? The ones that we got from here are the ones that are used in this part. So here we have kind of internal renewal in the same iteration. Here we use all history in the same iteration, and we only move from one like time lapse to the next one when we move to the next iteration, okay? That's the difference between the two methods.
So because see them probably have less error than the Jacobi.
We will see. I think there is, if I'm not mistaken, it mentions the convergence, or basically how close it gets to the solution. So the convergence of an iterative method can be calculated by determining as we mentioned, so the current value minus the previous value divided by the current value. This gives you the relative error. So let's see if they did this for the, I don't think it's mentioned here. It's expected, I would say that it depends a lot on where you start. So sometimes it might be that the Jacobi is doing better, depending on the initial condition that you start with, which is kind of like the first 3 values that you start with in case of 3 variables, as opposed to the Gauss-Seidel, right? So you cannot really say that always one of them is better than the other. It's just depends on what was the good. If you have a good start in terms of initial conditions, the Jacobi is going to get you the solution much faster. If you have bad start, then it's better to do, because that one does internal updates in the middle. So if I remember correctly, that's the difference between them. One important thing here is that the Gauss-Seidel method may diverge. Diverge means that it will not get you to the correct error, to the correct solution. So the error grows instead of being bounded and reduces from one step to the other. And this can only this can only be guaranteed not to happen if the system has something called diagonally dominant system. So if you go and look at the matrix A, you will see that in each row, the diagonal element of that row is greater than the sum of all the other elements in the row. That's what's written here. So if you go to the second row, then element A22, right, in the absolute, is greater than the sum of all the elements in row A except itself, of course. Okay? If this condition is true, then definitely the Gauss-Seidel is guaranteed to always converge. If it's not true, it might not, depending on your initial condition that you start with. Okay? Again, it says MATLAB. I hope now it's correct. Yeah, it is MATLAB this time. Yeah. Yes. So this one is a MATLAB actually. Finally, I got something which is not Python. So this is, I think this is the Gauss-Seidel, if I'm not mistaken. Yeah. And I also have the M file, so I'll pass it to you. Okay. Another thing is, I mean, it sounds kind of opposite to the meaning of the word, but the concept of doing relaxation is a way of enhancing the convergence of a numeric approach, particularly the Gauss-Seidel, for example, and the Jacobi, right? So the way to do the relaxation is that you add a parameter called lambda, right? And that parameter is typically between 1 and 0, typically, which is called the under relaxation case. I don't know if the over relaxation is desired in some other cases. But anyways, the parameter is typically between 0 and 2. So it can take any values from 0 and 2. And that parameter defines how you calculate the new value, how much in the new calculated value you weigh the previous value. So remember, when we are calculating, for example, x1 at this step, we only rely on x2 and x3, right? Now you don't only do that, you got a value which is new for x1, you go now and rather than just setting it to that new value, you take it back a little bit to be somewhere between that value of the new and its own old value. So you don't go immediately to the new, just that's why they call it relaxed. Interestingly, this causes, even though it's relaxation, it causes actually the conversions to be better. Of course, all these conversion, the reason I'm not addressing the conversion a lot in terms of how it's calculated is all these conversion operations, just for your knowledge, rely on something in the math called the measure theory. Okay, so the measure theory talks about when you have a certain value and a small epsilon deviation from that value, how can you calculate whether that deviation is going to cause a bounded approach or unbounded approach when you do certain operations, right? It's like a pure math stuff. I don't think it's useful. It's even beyond my own expertise. I know about the measure theory, studied some of it for my graduate studies, but not an expert in that domain. But I know how these things are done. It's not going to be useful for you at this stage. So what we really care about is that you always need to know the method that you are using. It's in terms of accuracy, conversions, and the number of operations that is done. Okay. Anyways, so going back, choosing the value of lambda equals 1. If you choose lambda equals 1, it means that you don't really use anything from the old value, right? And this is the case for normal, no relaxation. If you choose lambda smaller than 1, then this means that you have, so if lambda is smaller than 1, it means that you have, in this case, some fraction and a positive fraction here. So you take the new value as somewhere between the newer calculation and the older calculation, right? Now if, so that's gonna be in the middle between those two. If you take lambda greater than 1, then this means that you are much closer to this one because you are using a big weight here. And here you are subtracting a value. So it's as if you got a little bit after the new value, but being dragged back to being 1 lambda away from it by the older value, right? Just drags you back, but you are no longer falling in the middle. You are actually, in many cases, you will be falling outside, but the old value is just bringing you a little bit back, right? Last thing is the same approach, which is the Gauss-Seidel, can be actually used for nonlinear situations, right? Whether you use also the Newton-Raphson, you know the Newton-Raphson, it's used to figure out the roots, right? Can also be used for nonlinear situation. And this is an example of a set of nonlinear equations represented numerically by the, solved numerically, sorry, by using the Newton-Raphson approach. So it shows you that if you have a function, again, remember you have a set of unknowns, x1, x2. In this case, you have only 2 unknowns. And you have a set of equations in those unknowns. So equation 1, equation 2. In this case, 2 equations and 2 unknowns. But the equations are not nonlinear. So you are no longer able to represent them using matrices and use the linear operation that we studied before. So now in this case, if you want to use the Newton-Raphson, you go to the first equation and you write that, or you expand that in terms of the first partial derivative with respect to the first variable and the first partial derivative of the second variable. Similarly, for the second equation, you represent that second equation in terms of you expand it in terms of the first partial derivative of the first variable and the first partial derivative of the second variable, right? This is kind of, what you see here is kind of tailored for multivariable, okay? And then once you did this, now you have your current value of f calculated from the previous value of f, right? So the f in the first equation, the current value of the first equation at I plus 1, let's say I plus 1 is now calculated by the previous one, I, and using both the current and the previous value of x, right? Similar multiplied by the first derivative, and then the current and the previous value of x2, the second variable, multiplied by the first derivative with respect to that. This is the update for the first equation. This is the update for the second equation, right? And then from those, you can get the current value of x in terms of the previous value. Your final target is to solve for x. So that just rewrite those equations such that you can get an expression for x1 in terms of x1 previous, and expression for x2 in terms of x2 previous. And you end up with these nice expressions, which are easy to calculate because all these derivatives, you can calculate them if you know the functions, right? And you can evaluate them at any point. Okay? You keep iterating, so you get new value from previous value, you get new value from previous value, you iterate one more time until you reach some bounded change, then you assume that you are close enough to the solution. And this is another MATLAB program that shows how you can do that Newton-Raphson for multi-variable case. It's also nice to go through it and try. MATLAB removes all that effort of writing the full algorithm that we saw in the previous slide because it has already a function called fsolve. This solves a set of nonlinear equations together. And it uses the Newton-Raphson in certain setup. Otherwise, if it's not, it uses the Gauss-Seidel, so it tries several algorithms depending on the parameters of those nonlinear equations. Okay? The interesting thing is that this is quite unique because what you pass it here is a function. And that function is defined in terms of the parameters of your equation. So I'm not gonna go through the details, but if you go through those 3 slides, it's gonna show you how, including this example, so those last 3 slides is gonna show you how you can actually define that function based on the equations themselves, how we can define that, and then pass it to the fsolve. Okay? That's the objective of those last 3 slides, just to show you how to use the fsolve if you want to solve a set of nonlinear equations together. خلاص انتوا بتناموا وانا بنام والدنيا خلصت على كده صح؟ اعتقد كفايه.